Hi, I'm Shweta Gumpena, and I'm here to demonstrate the deployment of my Spark application on AWS EMR. This is as part of the second homework of CS 441. The documentation and code is all here in this repo. So the steps to set up the project as well as the different commands to run and the inputs and outputs are clearly stated in this section. And typically, the requirements of this homework was to perform parallel random walks on large graphs to simulate how man-in-the-middle attacks work. Each node in the original graph has the attribute valuable data that specifies whether a given computer holds some sensitive data. So the insider, a man-in-the-middle attacker, knows the original graph because the attacker is an insider itself. However, this person does not know whether the nodes that represent computers in the perturbed graph are authentic or not, making a mistake and choosing a honeypot, believing that it is a valuable data. Computer results in the security systems detecting the attacker and disabling the malicious program. So, so this project includes several steps of first creating the random walks in parallel and then compute and then going through each node of a random walk and computing the similarity score. And when a match is found, it is then checked if the original node has the valuable data. And if it does, then we decide if we decide to attack it. And this would result in either a successful attack or a failed attack. In the case of a successful attack, the insider was able to attack and draw valuable information from this node or the computer. Whereas when it's a failed attack, the attacker is busted. So here is a code base for this. So the main entry file is the main file, which has all of the which has the Spark application code. So to deploy it, we would have to first create the assembly jar. And to do that, I would be running this command. This is I'm mostly using this command to increase the space of the memory. In the meantime, when this is running, I can go over to AWS and S3. It's probably a little slow because the jar is also being created in the background. So I've created a bucket called 441 assignment 2 in US East North Virginia. And then I've also added a policy to this bucket so that it can be accessed over HTTP. This is the bucket policy that I've added. And I've created an input folder which contains the ngS file of the original graph, ngS file of the perturbed graph, and the YAML which has the differences between the original and the perturbed graph. These would be the input arguments to my program. And this is a folder for the jar that I'll be uploading once it's generated. In the meantime, I can show you the parameters that I'm giving, the configuration. So the first argument is the ngos file of the original graph. The second is the ngos file of the perturb graph, and the third is the YAML. And fourth is the output directory where we would want our resources to go to. And I also have a application.conf file, which allows us to give configurable parameters to our program. So I've defined the max walk length. This is as 10. This is basically the maximum length a walk can have. And a coverage of 0.9, which means I would terminate my program after 90% of the nodes of the perturb graph are covered. And a similarity threshold of 0.5 if two nodes have a similarity value greater than 0.5, then they're considered to be similar. And this is the file name of my results, which would typically be created in this resources.output folder. Some of the challenges that I faced while running this project, um, I'll just go over those. So I'm using Scala 2.13 and a Spark version of 3.4.1. I'm using 3.4.1 because although 3.5.0 is available, I'm using 3.4.1 because this is the highest version that AWS supports for Spark. And since I'm using JDK 11, um, certain dependencies such as sun.neo.cs are not available. These are only available in JDK 8. Due to this, I had to add these options in my build.sbt to avoid those errors. Also, Spark provides a different version of Jackson versus the Jackson that's already provided, due to which I had to override the Jackson dependency. Else it was giving version mismatch error when I was deploying it on AWS. And I also had to add this another command to get rid of the Jackson error. A jar of grabs underscore mitm underscore attack would be created in the target folder. I think in the meantime, I can also create a cluster. I would need elastic MapReduce to create a cluster. Go to create cluster. And then I can give 441 MIDM, man in the middle attack. And I choose Spark 3.4.1 because this is what my program uses. And I can go ahead and choose M4.large. Create a step. MIDM attack. Char location, I could give that once I upload it. So in the meantime, I can give the input parameters. So here this is, I think it's almost done. Let it complete. So the input folder. The first argument is the original graph NGS. The second parameter is the perturb graph NGS. And the third parameter is the YAML. Finally, the fourth parameter would be the output folder directory. And I'll terminate the cluster if the step fails. I'll go to my jar and see if my jar is ready. Okay, my jar is completed and it's in target Scala 2.13 graphs MITM attack.jar. I'll upload it here. Add files. Scala 2.13 graphs MITM. So this was just created. And then I can open it and upload. This would be my jar path. In the meantime, I can also run this locally and show the output. So my inputs are here. The original graph, perturbed YAML, and the output would be created here in resources.output. Okay, my jar has successfully uploaded. I will copy this S3 URI and give it to my cluster. So this is a jar location, given the inputs, and then terminate if step fails. I'll save this step, and then I would go ahead and choose my IAM role. And I think everything looks good. Spark 3.4.1, EMR 6.14, primary M4 large, and then one instance, and I would create my cluster. My cluster has started. So this will take some time to provision the resources and for the program to run. In the meantime, I'll run this locally and show with these parameters, that is these three input files and the output directory. So this is a configuration that I have mentioned, and I'm running it on JDK 11, and I'll run it. So this is completed. It would create the results file in the output directory. So here we're logging the nodes with valuable data. So these are all the node IDs of the original graph that have valuable data. And currently my application.conf runs on coverage of 0.9. That is, I'm covering 90% of the nodes. So this perturb graph has approximately 495 nodes. So 90% of that is approximately 445, I think. So once it reaches the 445 nodes coverage limit, we then terminate the program. So to reach so many nodes, it has done 341 random walks. Out of that, all of these are the nodes which have resulted in a successful attack. So we can see that 41 matches with 41 and 41 has valuable data. So all of these successful attacks would correspond to the ones that have valuable data. So successful attacks can typically mean that these are the nodes which have a match with an original one that has valuable data, as well as it is one of the um removed or unchanged node of unchanged node that we get from the YAML. And also a failed attack is something that when the attacker is trying to attack on an added or modified node, which is very similar to a node that has valuable data. So this is basically a honeypot, and when the attacker, which was basically kept to deceive the person, to make it look like that it has valuable data, because it's very similar to some other node that has valuable data, but it was just kept to deceive the person. So when the attacker attacks it, typically that node is not expected to be used by any legitimate person. So when someone accesses it, we know that that person is an attacker and we can catch the person. So with this coverage and for this graph, this has resulted in 41 successful attacks. This will vary from every run to every run, because the nodes are just picked up in random, because it's a random walk. These results do not remain constant for every time the program is run. So there are 6 failed attacks. And so the minimum number of nodes in a walk is 1. So this could basically mean its neighbor. After the starting node, its neighbor is already visited, so we terminate the walk. And the maximum number of nodes is 10. That is, it has reached the maximum limit that a walk length can have. And the mean number of nodes is typically 1.8 nodes on an average in every walk. And then the ratio of number of random walks resulting in successful attacks is 0.15. That is 0.15 walks have at least one successful attack in total. So let's wait for this to come up and running for us to see the results. And also the results have been, I've also shown the results in an Excel, which I've added to my README. So this is an example of the results that we just saw. And also, this is a graph that shows for different values of coverage, how does the number of successful attacks and failed attacks look like. So I've started with a coverage of 0.1. That is, only 10% of the nodes in the entire graph have been visited, which resulted in lesser number of successful and failed attacks. But as we increase the coverage, that means if more and more number of nodes are being covered, it ensures that more and more number of attacks are possible, and that could lead to successful and failed attacks, which also comes with a trade-off that if more and more nodes are being visited, there's a higher chance that that person can be caught, because hitting a system continuously, hitting every system in the network continuously would lead to that person being caught. So that's the trade-off. So this has changed to running. And if we see the steps, it's still running. Well, let's wait for it to be completed. So it is completed. We can go to S3 and check if the output directory was created. So we see that the output directory is created. And then we have the attacks.txt. So this has the similar information that we saw locally, the nodes with valuable data, the coverage, number of random walks, the successful attacks, the failed attacks, number of successful and failed, minimum, maximum, mean number of nodes in a walk, and also the ratio of number of random walks resulting in successful attacks. So this was about it. I will go ahead and terminate my cluster. And this was it. Thank you.